an arc of research. As a PhD student at MIT, working with Piotr Indyk, and he was really hardcore into theory. He was working on algorithms until he came to Berkeley, and he had the switch from algorithms to designing data sets, because it was clear at that point to very, very few people, including Ludwig, that it's almost always about data. It's not about the architecture. It's not about the algorithm. It's almost always about the data. And in spite of the fact that you get some things from the algorithm and the architecture, you get a lot more things, a lot more juice out of your training data. So they started with developing new test sets for CIFAR and ImageNet that were used for a bunch of analysis. But one of the most interesting sort of like findings there is that in spite of the fact that people have been training on CIFAR and ImageNet for years, the test set was in some ways uncontaminated. So they create a new test set, and basically the rankings of the models on the old CIFAR and ImageNet data set were completely preserved on the new one. And he continued on to do a lot of work on creating big data sets for different modalities and different sort of like models, bringing a lot of people together. He's, I would say, one of the most impactful researchers of our generation, precisely because of his taste of picking the right data problem and picking the right team to work with him. So DataComp is another very successful project. And today he's going to talk about OpenThoughts, which was the first open dataset for reasoning models, and Terminal-Bench, which is an evaluation that tests effectively the following. So you have a model, but now you give it access to your computer or your terminal, and then you ask it to solve really hard tasks. And Terminal-Bench basically tests how good these models are, and has become one of the key sort of benchmarks that all companies, including OpenAI, Anthropic, Google DeepMind, showcase the capabilities of their agents. And we're super excited to have Ludwig today here with us.
Cool. Thank you very much. Thank you for the very kind introduction. Really excited to finally make it to Madison. As we just chatted, the first time I was here was only virtually, 2020, in the pandemic. So it turns out in person, it is much nicer. It's a great place to be here finally. Okay, cool. So today I'll tell you about work my group has done sort of like end of 2024 throughout 2025 on data for training and evaluating agents. And if you have any questions throughout the talk, please just raise your hand or just interrupt me. I'm super happy to make this as interactive as possible. Cool. Okay. Just to make sure that we are on the same page, what do I mean by agents and why do I think this is important? I think we are mostly on the same page here, but just to recap, sort of like a lot of excitement in AI started with the release of ChatGPT, end of 2022. And for the next 2 years, let's say until end of 2024, most people interacted with AI, with language models, in a chatbot interface. You ask the model a question, it gives you an answer, and the answers got pretty good and it was already really useful. But there was sort of like a key limitation with this. And this was that you always need the human in the loop quite closely in order to actually do longer running work. Like concretely, this manifested in like people spend a lot of time copy pasting commands between ChatGPT and the terminal, and then something failed. They copied the terminal output back into ChatGPT, and that helped them overall, but it also limited the throughput. So the question was, okay, if we want AI to have larger economic impact and work on more challenging problems, can we have the AI, the language models, directly work with the computer? And like for me, this is always what I think about when I say AI agents. Sort of like instead of having the user closely in the loop, now we let the model directly use the computer, do things for a long time horizon, and solve complex tasks. And this really started to gain traction in 2025 with, for instance, AI for search, and then this explosion of interest in coding, like Codex and Claude. Okay, so this is clearly a very important topic. And now today we'll talk about the data side of agents. First on the training set side, OpenThoughts, and then a little bit OpenThoughts agent. The follow-up project for training agentic models. And then we'll talk about the evaluation side, Terminal-Bench, which is to see, as Dimitris mentioned, how good are these models in command line environments. Okay, so let's get started with the first part, OpenThoughts. And before we talk about the agent things, a little bit towards the end, most of this is actually going to be about reasoning models. Again, just to put things in context here, Initially, when the models came out, you would ask them a question. As I said, they give you an answer, and they will give you the answer basically right away. They didn't have the ability yet to think for a long amount of time, for a long time before they would answer a question. And obviously, as humans, intuitively, for a complex question, we need some time to think. And sort of like there was this breakthrough towards the end of 2024 from OpenAI, the O1 series of models, where they figured out how to train models to do a lot more thinking, chain of thought, before they give you before the model gives you an answer. And this led to a lot of progress on challenging benchmarks. So one of the most widely used benchmarks in this context is AMI24. This consists of sort of like high school level Olympiad problems, think like IMO, the International Math Olympiad, and similar ones. And what you can see is that the models at the time before O1, they were pretty bad. GPT-4o, state-of-the-art model, 13% accuracy. And then this O1 model from OpenAI on the same benchmark, roughly a year later, got 83%. So a massive jump in accuracy. Similarly, competition-style coding, massive jump from 11% to 89%. And also nice progress on challenging question answering problems in the sciences, like GPQA, 56 to 78. So this was a big, big jump, right? If you follow these benchmarks, large double-digit improvements usually mean some breakthrough happened. And the obvious question was like, how do you actually train good reasoning models? Massive jump in benchmarks, but this was already the time when the frontier labs wouldn't really tell you anymore how they trained their models. So the goal of OpenThoughts was to build training sets for training good reasoning models to make progress on exactly those benchmarks, so we can understand better in the open what goes into these reasoning models. And this was a large open source collaboration with a lot of people. Unfortunately, I can't tell you about all of them. So let me just go through the first author students here because they really did most of the work. Atosh was a PhD student with me at UW and Stanford. Now he's at Anthropic. Ryan, he was an early employee at Bespoke, the startup Alex DeMarcus co-founded. Cedric was a research scientist at Toyota Research. He's also now at Anthropic. Nigin just finished her PhD at Berkeley, working with Alex DeMarcus, joining Anthropic soon. And George was a PhD student with Alex back at UT Austin. He's also at Anthropic now. Cool. And as I said, many, many more people from many more institutions. And what I want to do in this talk, tell you a little bit about the journey of how we built the state-of-the-art reasoning data set. And I hope this also helps illustrate the research progress in this like large open source collaborations. And I think this is also representative of how research works at sort of like frontier model scale. In some ways, not in all ways representative. And so like there's several steps here along the way. Our final data set, was called OpenThoughts 3. This is called 3, it already means there's a 1 and 2 before. But at the beginning of this journey, we'll actually start with the DeepSeek R1. And DeepSeek R1 was a really important step here, came out in early 2025, big splash. And this was really important because they were the first ones who published an open training recipe for training O1 level reasoning model. They put out their open weight model. They didn't put out any training data and no training code, but in their paper, they documented quite accurately how you can train a model like that. So to recap, let's go through this quickly step by step here. So the starting point for all of this was their base model, DeepSeek V3. This came out in December 2024, was already a super nice paper. They're doing great research at DeepSeek. And what they did in their DeepSeek R1 paper, start out with their base model and then start applying RL, specifically with this GRPO algorithm, to train their base model to produce longer and longer reasoning traces in order to solve these math and competition coding problems in a better way. And like they did this for a little bit with no prior SFT, got some reasoning data out of it, and then they used these reasoning traces and started this entire process again from the beginning, where they did some SFT on their base model. Then they did more RL to get the model better at these math and competition problems. And at the end, they had 600,000 examples of the model doing well on these challenging math problems. And then they again started all of this from scratch. So they threw away this model, kept only this SFT training data, and fine-tuned their base model, again on these reasoning examples, plus 200,000 extra data points to make the model a good model. That was their reasoning model. They did a little bit more RL at the end, but this was mostly sort of like, let's say, chatbot RL, to make the model a good chatbot that didn't really improve the reasoning much. And this was their final R1. And they did this at quite large scale, 670 billion parameters. So this is, from an open source reproduction perspective, a bit of a problem, right? We didn't have to compute to train a 700 billion parameter MOE model, but we thought, okay, overall, this is like a nice template and a good starting point. And the other thing they did in the paper was they showed that you can get really interesting reasoning behavior already from distilling from their large model into much smaller open weight models. Specifically, they took their DeepSeek R1 model as a teacher and then created reasoning data in order to distill the reasoning ability into various Quen and Llama models. And then when you look at this table here, this 7B model, fine-tuned on their distillation data, is already comparable to O1 Mini, a little bit worse, but getting in the same ballpark on AMI 24, right? This was this imported math reasoning benchmark. And with the 7B model, they got roughly in the same ballpark. And with their 32B model, so Quen 32B, fine-tuned on their reasoning data, they actually got higher accuracy numbers than O1 Mini. So we thought this was really interesting because this showed two things. The first thing was you can get interesting reasoning behavior already at much smaller scales. And you can do so via fine-tuning on a small amount or comparatively small amount of reasoning data, like a few 100,000 reasoning traces. And we thought this is a really good starting point for us to sort of like start exploring this reasoning space. And very concretely as a goal, what we set ourselves, can we match the performance of these DeepSeek R1 distill models? Can we build reasoning data that is as good as the reasoning data DeepSeek uses? So concretely, the goal was to reproduce in the open this lower part of their training. Okay, cool. So that's what we set out to do. And we obviously were not the only ones who were interested in this. In early 2025, reasoning was by far the hottest thing in AI. So various other teams also started working on this. And one of the earliest reproduction examples there came from Berkeley, specifically the SkyT1 model. And what they started doing successfully was set up a basic pipeline of sort of like 3 steps, some form of data generation. They used the QWQ model from the Quen family to generate the SFT data, then train on an open weight model. They used a relatively small amount, 17,000 data points, and then evaluate on these standard benchmarks. And what they could show is that their model at the 32 billion parameter scale on AMI 24 was getting 43%. So in phase over the base model is only 17% and already comparable to this preview version of O1. And this was a very nice starting point. There's a lot of work followed this basic pipeline here, of like generate or experimental workflow, generate some data somehow for SFT, train on an open weight base model, evaluate on the standard benchmarks.
Ludwig, do you remember what the datasets were for that? Was it like pre-existing or they came up with them?
I think this was pre-existing ones. We'll get to this in a second. Good question. I think this was similar data as the bespoke Stratus training set and model quickly thereafter. So, okay, the SkyT1 thing from Berkeley came out, and let the bespoke starter were like, okay, this is a good first step, but they already had ideas for building a better data pipeline. So let's look into this a little bit. And specifically, they made 2 changes. They swapped the teacher. Instead of QWQ, they now use DeepSeek R1 because this is a better reasoning model. And they changed reasoning trace rewriting steps. So in the SkyT1 paper, they used a small model to rewrite some of the reasoning traces. And they were, okay, let's not do that. They also changed the rejection sampling. Overall, their pipeline looked like this. They had 3 different data domains, code, science, and math. and used existing data sets by feeding the instructions into a teacher model. Then you get the reasoning traces out of R1. And then for each of the 3 domains, they had a separate filtering pipeline. Basically, do you keep an existing instruction answer pair, or do you throw this out? Depending on the domain, there was a different rejection sampling approach. Then you put all of this together. That's your data set. And then they did SFT on it, and they evaluated. And overall, the improvements in the data did also show an improvements in the models. So their Stratus 32B model was now better than SkyT1 by a nice margin, and getting close to R1 distal. But on some other data sets, this was also clearly worse. Like if you look at Live Codebench, which is competition style coding, and then specifically the harder part of the data set, there was a noticeable gap to R1 distal stuff. Okay, but overall, all of this research at the time, this is why I'm going through step by step, was sort of like a nice example of the open source communities of like collaborating and step by step making progress together on these benchmarks by building on each other's insights and data sets. And when we looked at this in OpenThoughts, we were thinking, okay, this is all a nice start, but one dimension that's clearly missing here is scaling, right? We know that scaling is really important, and concretely, we know that the DeepSeek R1 paper trained on 600,000 to 800,000 data points, and Bespoke Stratus was still 17,000 data points. And so very pragmatically speaking, if the goal is to match DeepSeek, we should scale up these data recipes because there's probably some juice left simply by scaling up. And this is what we did. We basically used more data sets for these different domains, same teacher, same infection sampling pipeline, and this was our first OpenThoughts. So we went scaled up by a factor roughly like say 8 to 10 to about 100,000 data points. And yeah, I mean, we made progress. Pragmatically speaking, this was just the first version. We just want to see, okay, by scaling, do we actually get better numbers? And the answer is yes. So our 7B model was a nice improvement over Bespoke Stratus here on AMI 24 from 23 to 31. But still substantially behind the DeepSeek data, right? At the 7B scale, they got to 60 on AMI 24. And then similar on Live Code, but again, on the hard problems, 7B scale, DeepSeek R1 is still 15%, we were at 6.5. So again, one step forward, but not quite there yet. Same story on 32B. Let's skip this in the interest of time. Was state of the art among open data at the time, but not yet at R1 distal level. But we were okay, thinking, okay, good. So we have 100,000, but DeepSeek has 600,000. So it's still not a fair fight, right? We need to scale this up further to understand at the current data quality level we have, if we scale this out, can we match DeepSeek? So how I always think about this is like 2 dimensions. How much data do you have, the scale dimension, and then how good is your average data point, the quality dimension? And at this point, a reasonable hypothesis was maybe we are just behind because of scale, and then we should just keep scaling this up. And that's what we did in OpenThoughts too. And the good news was that at around this time, as I mentioned, this was the hottest thing in AI. Basically, everyone was building reasoning data sets. And so the open source community accumulated many data sets from different groups with reasoning data, and it became quite dissue and a little hard to follow. But we were thinking, okay, if we just take the best data out of all of these things that are already published, can we match DeepSeek? And so what we did was a big experimental study where we just took all of these data sets, evaluated them one by training models on them. And we thought, okay, let's just keep the best data sets, take those examples, put them together, and see how far this gets us. And like, where do all of these data sets come from? It's really a big zoo of data sets that come from textbooks, other things like exams, online question answering websites like Stack Overflow, fully synthetic data pipelines where the instructions are also model generated. People really tried everything. And then this led us to OpenThoughts 2 data pipeline, which finally got us to 1 million data points. And so basically, how does this look? We took the top data sets in the code domain that we found, put it together with the top math questions we found, did some deduplication because there was now some data sets appearing in multiple of these compound data sets, annotated again with DeepSeeker 1, put in even more math data because this looked good, and then we combined it with our previous data set, and that was OpenThoughts 2. And to be fair, this is getting pretty messy. So like the approach here at the time was simply, oh, well, everyone wants to build good reasoning data sets. We want to stay state of the art. Let's just see if we can finally match DeepSeek by putting everything together. Overall, it's a bad sign when your diagram becomes recursive. I think that means probably more complex than it should be. Yes, question?
Do you perform any data selection within the particular data sets that you select, or do you just take all the data from?
Question, not yet. We will get to this, but for now, we really just put the things together. Like for context of like the time between these OpenThoughts releases, we're sort of like maybe on the order of like 2 to 4 weeks. So it was pretty fast iteration. And so we didn't have time to do as detailed ablations as we would like to. Any more questions?
So I have a question, building up on the previous one. So you mentioned in OpenThoughts 1, there were roughly 100K data, and then you went all the way to 1 million, right? So how important was the diversity of the data? Or like, was it a particularly important to be from different sources, or have exactly the same methodology of collecting them, just scaling?
It turns out diversity is not that important. We'll get to more experiments on this later. At this point, we really didn't know yet. We just wanted the number to go up. And in a minute, we'll talk about some of these ablation experiments we did to understand more systematically what parts here really matter and what are maybe some principles behind the data curation. Good question. Okay.
Yeah, I have another question, related question. This is Ramya Vinayak on Zoom. This is related to, I guess, the past 2 questions. In the OpenThoughts, there was one of the arrows, like, said science. Are there general science kind of questions? And with respect to that, like, that is the only box that I see that there was no verification. So I was wondering if you had comments on like the quality check, like in terms of like how important is checking the quality, and when it comes to, I guess, non-math or non-coding, are there ways people try to do verification where there is not an easy ground truth or like unit tests that you can run?
Yeah, okay. This is a great question. 2-part answer. We'll talk about the role of verification and the importance in these data pipelines in a little bit when we talk about OpenThoughts 3. And sort of like, what do people do? I think you're right. Sometimes it's hard for this to be like an exact check, like, oh, does this program pass unit tests? You can check this easily. Sometimes people use LLM as a judge to check whether their answer to a science problem is correct or not, but obviously this also has limitations. Good. For now, let's continue and see where did we end up with OpenThoughts 2. So at the 32B scale now, OpenThinker 2, which is the model we trained, was again a nice step up compared to OpenThinker 32, OpenThinker 1 32B. So 9 percentage point gain roughly on AMI24. And now we had finally made it to the point where we were better than the R1 distal model. So they got 75, we got a little bit higher on AMI24. And basically for all of these benchmarks, we were either better or sort of like in the same ballpark, maybe a little bit worse, but overall, Live Codebench now same number, AMI25 even a little bit better, and so on. So we were super excited about this. We had set this goal, match DeepSeek, and now that we use similar amount of data, we got the same performance as their reasoning fine-tuning data set, which was super nice. But then, as I mentioned, the data pipeline at this point had become really messy, and we thought, let's clean this up, because as people here already asked, there are good questions what actually matters in these pipelines. And we were thinking, okay, maybe we can do even better, because in my experience, always, if you have a really messy data pipeline that grows over time, this is often a good starting point for doing more systematic experiments and build an even better training set. So in the past, my group had done this in different domains successfully. So we did this datacom project Dimitri's mentioned for multimodal models, specifically clip models in 23 and 24, and then 22 and 23, and then same approach, careful data curation leads to better models, also for language models in the DCLM project. This was 23 to 24. And we thought, okay, this was a good paradigm. Let's just do the same thing again, but now for reasoning training data. So to recap, so like, how does this pipeline look? You start out with some source questions, then you mix together questions from different sources. You filter the questions, you generate answers from a teacher model, then you filter maybe again based on the answers. Somewhere in the pipeline, you also need to select your teacher model, next your final training set. And within each of these steps, there are again many, many different questions that one can study. Like, how do existing instruction data sets perform? Does synthetic data work? Can you rewrite instructions? How should you do instruction filtering? As we said, does diversity matter? Should you take data from multiple sources? What's the impact of the teacher model? And so on. And we tried to answer these in a consistent experimental setup so that ideally the answers to all of these parts would stack up and would allow us to build an even better training set. And then what we got out at the end is sort of like summarized in these scaling plots. So on these plots, we have x-axis dataset size, y-axis performance, higher is better, and an AMI 25, again, math competition dataset. The final dataset we built, OpenThoughts 3, is this red line here. And the nice thing for us was when we put this out for NeurIPS last year, or around NeurIPS last year, this was again state-of-the-art model. In the meantime, we had gotten tough competition from NVIDIA. They built a very nice data set, Nemotron Nano specifically, and this is the blue line. And before us, they were the state-of-the-art open source reasoning data set, but we were better than them. The nice thing is also in this plot, you can see we are not just better because of scale, right? Overall, you can think OpenThoughts 1 and 2, we got the best reasoning models because we had the most data. Scaling is important, but now with our improved data pipeline, the red line here is on top for all intermediate data scales also. So we also improved in terms of quality now. Similar story, Live Codebench, basically best line. There's this dip here at 300K, and we still don't know what happened, to be transparent. Like, this gave us a lot of anxiety because when you do these experiments, you scale up, and because at smaller scales, much cheaper to iterate, much cheaper to experiment, you can try out many ideas, then you scale up the best ones. And for some reason, the 300K data point, it went down. And we were like, okay, should we scale this up to 1M? Before, the scaling trend looked super good. So we did a lot of tests, experiments to figure out what was going on. And to be fair, we never really did. And then one of the students was like, let's just run this at 1M, at 1 million, and see what happens. And it turned out really nice again. So there are many, many open questions coming out of this. I don't want to say in any way that we have figured out all the principles here. This is more like, okay, this is one recipe to get state-of-the-art training data. I think understanding more of the principles behind it will probably help us build even better training sets. Okay.
I have a few questions. Are you going to talk about ablations?
Yeah, the ablations are next. So I want to just start out with, okay, where did we get? And okay, there's this like big table here with all the results. We're not going to go look at all the numbers. As I mentioned, so like on aggregate, we had the best. One thing that was nice was at the end of this entire thing, we looked at a set of held out data sets, because one thing that is worth thinking about is when you use these data sets a lot to pick your training data, maybe you're building something that's only good on AMI 24, maybe only good on MAP 500. So we had a set of held out test sets that we only looked at the very end. And the nice thing is like AMI 25 had just come out. So we also do well on this. This was held out by the definition, and a recent Live Codebench update was also held out, and we're also doing well on that.
I just want to comment on the 300K. So I through some experiments with AME, it's a pretty noisy data set.
Yeah.
I think if you were to do like 64 repetitions or 128, maybe you will see a little bit.
You mean these repetitions at evaluation? Or?
Yeah.
Yeah, I think we did many evals.
Okay.
We did many. I don't remember how many, but I think that we ruled out.
Okay. I guess the other thing I want to ask, so the data set, you filtered only for correct answers, correct?
Let's get to this in a second.
Okay.
Okay. Blah, 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 better scale, better data. Okay, now let's go through some of the findings that we had along the way in these pipeline stages. And I think the high-level takeaway here is what matters the most is question quality. So among all the different pipeline stages, we saw the largest range and benchmark scores come from the different data sources. As I mentioned, this is this big zoo of existing data sets that we experimented with, also some of them our own. And I can't tell you any principles. We tried a little bit to figure out what makes a training set good. Pragmatically speaking, the thing to do is evaluate many data sets at small scale, pick the best ones. They're usually also the best ones at larger scale. Like concretely for code, we found that something from Stack Exchange, specifically the Code Golf Stack Exchange, was the best. And then there's a lot more detail in the paper, but at a high level, yeah. So like the range you see in terms of scores here from 38.8 to 21.6 by varying the code question source is really large. So that's the most important part of the pipeline. Then now going to this diversity question, should you get data from multiple training sets or focus all of your data budget on the few best data sets? And the answer was very clearly just take as much out of the best training sets you have. So like diversity in our experience here using different data sets does not help. Like concretely,
if you mean top, this is not about the teachers, just about like the data sets themselves, right?
Yeah, exactly. So basically we had our math data sets, you ranked them by performance individually, and then we compare just taking the top 1 versus a mixture of the top 8, and the mixture of top 8 is worse and top 4 is worse. So overall, the way I think about this is that it seems like data quality for math here is basically one-dimensional. And if you put in lower quality data sets, it helps with diversity, but we're not really, it's not clear what diversity exactly means there anyway. And what you're effectively doing is you're diluting the quality of your higher quality training set. So for us, we just went with the top data sets in each domain. One thing that helped a bit was filtering based on the questions. So we used various methods like using a language model to do selection based on response length. You can ask LLM, simply ask a language model, is this a good question or not? You can set up a binary text classifier, for instance, fast text, positive being a high quality data set, negative being a low quality data set. And so we explored also different strategies for different domains, like for code. You can ask a language model, hey, how difficult is this? Or maybe this was not, sorry, I don't think this was asking a language model. This was selecting difficulty based on whether models could solve the questions. Again, lots of detail on the paper on this. It's an important step of the pipeline, not as important as the initial instruction quality, but definitely something that's worth iterating on. One thing that I found interesting was that you can stretch out your high quality data by sampling multiple answers for the same instruction. Initially, I was skeptical about this because I thought, oh, if you use the same instruction multiple times with different answers, this is maybe too little diversity and the model won't improve broadly to generalize to new data. But one of the students, Ada, she was just very happy to try out all the ideas. And this is often the right approach here. So like try out many things, iterate quickly through ideas. And it turned out that we could sample up to 16 answers from the teacher model for the same instruction. And this is great because, as I mentioned earlier, overall data quality seems to be one-dimensional here. So if you can sample multiple times from your best data sets, you can stretch those out further and train more on your high-quality data. next point was around answer filtering. This has come up. I think Dimitri's just asked about this, like, did we do any filtering based on correctness? And here, the surprising thing was that doing no filtering based on answer correctness actually performed the best. Like, naively speaking, you would say, okay, maybe a reasoning trace, or it would be natural to expect that a reasoning trace that actually leads to the correct answer is better than a reasoning trace where the model gets the answer incorrectly. We experimented with a couple of filtering approaches, and no filtering basically performed as well as anything else, if not better. And one intuition I have for this is that in the end, these reasoning traces can be several thousand tokens, and there are many individual sort of like reasoning steps in these long reasoning traces. And for the model, it's more important to learn how to produce long reasoning traces to begin with and get these many intermediate steps right, than whether these intermediate steps lead to the exact answer. So in a reasoning trace that's with the incorrect answer, it could be that 99% of the steps along the way are still correct. There's one mistake somewhere, but overall that mistake doesn't seem to affect the model that much. It's more about sort of like the journey in between, the tokens in between. And for that, it seems like the teacher models, they're pretty good on average. Yes.
Right. The question here is, did you control for after filtering and the no filter dataset size? This is why we have no filtering, not compute controlled, and random filtering. Yeah, I think some of these variants we put in order to control for dataset size. So also if you control for dataset size, yeah, okay. Because one mechanism would be that maybe if you filter out bad answers, you just have a smaller dataset, and then you put in less flops and it sees fewer examples. We did control for this with random filtering.
I guess just to add up to or follow up on this question. So it would be kind of interesting. I totally agree with what you say, because basically the point is you want to teach a skill to the model,
exactly.
Skill of reasoning, and whether the bit of correctness is 0 or 1 doesn't matter as much. But you would think that perhaps, well, there's also two kinds of failures. There's cases where there's no end of thing at all, where the model just keeps on going, and there's cases where it actually stops and the answer is correct or incorrect. I would like to think of an exchange rate between correct and incorrect chains. Have you guys figured it out at all? Like, so what I mean by that is, like, if I were to train on a mixture of n correct versus m incorrect, what would you see as a final accuracy on it? Like, how much is the XSAME accuracy between the two? Like, can we pinpoint the value of the correctness bit somehow?
Good question. I think we didn't have time to experiment for any of these individual things in that much depth. I think, as I said, this is like, I think, a recipe here to get to high quality reasoning models. It's not, the paper's not going into that much depth for each individual thing. Like, we could write a paper just on this. I think understanding is better. I think what you outlined would be a great experiment. So let me know when you know.
A follow-up question
good.
here. This is super interesting. So I was wondering, like, in terms of, like, when it comes to filtering, there is like filtering for the final answer, but there is also filtering for there is also the quality of, like, the reasoning traces themselves, right? Like, so is the idea here is that because these reasoning traces are being generated by a larger reasoning model, that these reasoning traces are of maybe there are like lot of the reasoning steps are correct somehow. Is that the assumption, in the sense that if we had really completely random reasonings that didn't really were not very good quality, then we wouldn't necessarily expect it to work either, right? So there is some quality that is needed, or maybe, like, I don't know if you have experiments on that.
No, definitely. I think this intuition that the reasoning trace quality matters is correct. Like, better reasoning models in the end do give you better reasoning traces, but it's also not as one-dimensional as that. Actually, this is a nice segue into the next slide here, where we experimented with different teacher models, right? Like, at the beginning, I said, back when they did the bespoke data set, they switched from QWQ to DeepSeeker 1, because DeepSeeker 1 is a clearly better reasoning model. If you look at these benchmarks, DeepSeek one gets high performance. And at the end of this, we were like, okay, we should also do a careful ablation of the teacher model. And then it turned out that QWQ, while it's a worse reasoning model, actually gave us better performance. So it is not a terrible reasoning model, not as good as DeepSeek, but gives us better training data. And we also don't know why that is. So one hypothesis is that QWQ is from the Quen family, our base model is from the Quen family. Maybe there's some on-policy thing going on that your teacher model being from the same model family as your student is better. People did some follow-up work, and my understanding is that this is not true in general. Sometimes out of model family teachers can work better than in model family teachers. So this is one of those things. In the end, I unfortunately can't tell you precisely what makes good reasoning data. The takeaway here is that, again, good to explore many hypotheses and be very sort of like empirical in your approach.
Do you remember the CO2 average lengths between QW?
That's a great question. No, I don't. I hope we have that in the paper. I don't remember.
I guess my conjecture may be somehow a function of that, because, for example, GPT-OSS is a strong model, but reasoning traits are much shorter.
Yeah.
So it's not a good teacher for SFT. So yeah, just curious if it's just the length or something.
Yeah, it is a good question. I don't think it's just the length, because we also did just selecting based on shortest answers here, and that didn't help us either, or didn't hurt that much. So yeah, lots of work for follow-up research. Let's put all of this together. How did our final data pipeline look like? So we had all of these source data sets at the beginning here, quite large. And then we did a lot of filtering. We filtered the questions, as I mentioned. We did deduplication among these different data sets. Then we randomly subsampled, generated multiple answers, and that gives us our final 1.2 million data set. So maybe one takeaway here is that in the end, this is a quite aggressive filtering pipeline. Out of these many initial questions, only quite a few are left at the end that we then upscale and put into our training set. Cool. Okay, so let's quickly summarize here and go to the next part. As I said, this is a state-of-the-art recipe at the time, at least middle of last year, for fine-tuning reasoning models. Lots of interesting findings and design choices that we would like to understand better. One thing that was nice to see, that OpenThoughts became a widely used data set. So each iteration that we put out became a #1 trending data set on Hugging Face. OpenThoughts became part of the almost free training set, specifically the reasoning training set. And then Thinking Machines, when they put out blog posts about Tinker, their fine-tuning API, they often use OpenThoughts in their examples. Cool. So if you want to learn more about this, go to openthoughts.ai. But for now, we're going to change gears a bit from training data to evaluation data. Okay. So let's go back to this high-level distinction between chatbots and agents and ask, what are the implications there for evaluation? So back in the good old ChatGPT chatbot days, evaluating the models was relatively easy in terms of infrastructure. At least sort of like the API was simply put text in, text comes out of the model, and then you grade this somehow. I think one good paradigm always was multiple choice, question, answer, easy to grade, usually single turn interactions. Lots of cool stuff we learned from benchmarks like MMLU. Relatively simple infrastructure. When you want to evaluate agents, a lot of these things become more complicated. So now you want to have the agent interact with an environment. So you need to sandbox it. Often people use Docker containers for that. Instead of a single turn, now the model interacts with the environment over multiple turns, does tool calls and so on. And the correctness tests also become much more tricky, because now at the big end, you have like a large code base or just a Docker container final state. How do you check whether the model did the right thing or not? It's not as simple as a multiple choice answer. Nevertheless, people started building some really nice benchmarks for this agentic paradigm. I think the most impactful one is probably SVBench for software engineering. And sort of like around the middle of 2024, I was thinking, okay, we have good chatbots for AI progress. The next thing we need to figure out is how agentic are the models? How good are they at long-running tasks? And I thought if we want to build a benchmark for that, the terminal would be a really good environment for the following reasons.
The first thing was that, well, terminal command lines, they are text-based. And in the end, the language model is clearly best at text-based reasoning and working in a purely textual domain. So at the time, the models couldn't really do long horizon tasks. So I thought, let's make it as simple as possible for the models and do everything in text. The next thing was command line is good because it's very powerful. There's a ton of stuff you can do simply from the command line. You can use editors like Vim in order to build complex code bases, do all sorts of subsystem administration, schedule tasks, do data analysis. So while it's maybe more limited than a graphical user interface, it's still a very powerful way to use a computer. And it's also economically valuable. There are a lot of tasks where people interact with the command line a lot in order to do meaningful work. And the other nice thing was that, as I mentioned, there are these sandboxes like Docker, so there was good infrastructure for sandboxing agents in a terminal environment. And overall, this is also very much the direction the industry moved in. So like 2024, 2025, the first command line agents like Codex, Claude Code, and so on emerged. Okay, so what concretely is Terminal-Bench now? In a nutshell, a Terminal-Bench task consists of the following parts. You have a Docker container. So every task comes with a Docker file describing how to build a Docker container. It has a task description and a YAML file. For instance, here, the task would be re-implement the COBOL program located in blah, program.cobol in Python, and so on. And then a task also needs to have tests associated with the task. These are hidden from the agent at the beginning. And then what we do is we set up the Docker container, install the agent in the Docker container, and tell it, go. Here are the instructions, do the job, do the task. And then once the agent is done, or we reach some timeout, we copy the test scripts into the container, run the test scripts, and then the test scripts decide, hey, the agent did the right thing, or no, the agent made a mistake. Okay, so conceptually, this is simple. The hard part now is make many good tasks. So what we did is, again, we crowdsourced this into a large open source collaboration. The people leading the project were Mike Merrill, at the time my postdoc at Stanford. Now he's at Anthropic, and Alex Shaw. He works at the Law Institute that Andy Konvinsky started, and he's also one of the co-authors. And the two did a fantastic job, Mike and Alex, shepherding this large open source collaboration. And there are so many authors because we wanted to get many tasks. So we set up the incentive system as if you make 3 tasks for Terminal-Bench, then you become a co-author on the paper. That actually worked quite well. Good. So what is in Terminal-Bench? In the end, it was 89 high-quality tasks, some sort of like examples of things that are in there. Couple tasks that agent needs to build complex software from source, like for instance, build PyTorch from source. And if you've ever tried doing that, lots of complicated dependencies takes a while to do. Then various tasks where you need to train and tune classifiers, scientific workflows like DNA assembly, and so on. And one important part was Mike, Alex, and Nicolas Carlini, who helped a lot, they put a lot of work into verifying that these tasks are high quality, because with these complicated setups, at the end, checking whether the Docker container is correct or not, is not correct or not state, is very subtle. So we spend a lot of time making sure this is high quality. But then the nice thing was, because people recognized this is a high quality benchmark, many frontier labs quickly adopted this. So the first model that put us on their model card was the Claude 4 release. Dario highlighted this with numbers on SWE-Bench and Terminal-Bench, the model. And then after that, Qwen, OpenAI, Google, the Terminal-Bench is now often one of the sort of like highlighted benchmarks when a new model comes out. And so it's also nicely, the open source community around this has grown nicely. And on our Discord now, we have over 3,000 members who are helping with the follow-up benchmark around Terminal-Bench. Cool. So how did the models do overall? I think this is a very nice plot, because this shows this really rapid progress we've seen last year on agentic tasks. So this was before the benchmark was out, but hypothetically, Claude 3.7 Sonnet, this was February 2020 or March 2025. Claude 3.7 Sonnet would have scored less than 20%. And by the end of the year, we had Opus 4.5.
and Opus 4.5 at around 60% accuracy. And I think this nicely reflects the fact that by the end of last year, many people really felt like agentic coding is really taking off and makes them a lot more productive. I think this really nicely maps to progress on this benchmark here. And this is the current leaderboard. It's not actually current. Every time I give this talk, I need to update the slides. And today, I forgot to do so this morning. This is GPT 5.4 still, but it gets 80% accuracy now with the Forge code harness. This is a nice improvement. I think 5.5 with the Codex harness now gets 83 or something. And Claude Mythos, when they ran this at Anthropic on the updated Terminal-Bench 2.1 task set with somewhat increased timeout, it gets over 90% accuracy. Basically, from our perspective now, this benchmark is almost solved. So Terminal-Bench 2.1, this is some fixes to the Terminal-Bench 2 tasks that had bugs. And the models can do these almost perfectly. Yes.
So I think the amazing thing about Terminal-Bench is I would call it a API complete benchmark in the sense of basically almost all interesting tasks can and probably should be implemented through a BAS terminal. It's like a mega tool where you do whatever you want, right? One thing that I'm curious about is sort of like selection of tasks because of its generality. Like somehow I think of Terminal-Bench first as an environment, and then you select a bunch of tasks that you actually test, right? And because it is sort of like a rich environment, you could densify everything. Like you could turn AI into a Terminal-Bench task. And so, what exactly is Terminal-Bench measuring? And how do you think of sort of keeping the scope such that it's reasonable and it reflects something in particular versus something that's super general and it's kind of like hard to argue about?
Yeah. Okay. This is a great question. Maybe sort of like a three-part answer. One is in the end, there's a trade-off between building a really nice diverse benchmark and being opportunistic with the tasks you just get from the community. In the end, getting to 100 tasks was already a lot of work. I would have liked it to be 100. It was 89 because at some point we were like, let's just ship this and we want to do the next thing. So like I think there's a compromise between like being super representative and seeing what are actually tasks we got good submissions for. And we did want to balance broadly that this is actually interesting tasks. For instance, we got, I think, 5 to 10 tasks that were the model needing to navigate a complex maze on the command line.
Yep.
And at some point we were like, actually all these maze tasks are just games and we don't want games. We want like real work that people would do. So I think for TB2, we threw out all of the mazes. So we do some moderation. But what is the perfect set of tasks? I don't know. Since you mentioned everything can be converted to Terminal-Bench tasks in principle, yes, 100% agree at a high level. I think of this as a computer use benchmark. And one project we did for this NeurIPS was this Harbor adapter effort. So we built Harbor as framework to do the infrastructure for Terminal-Bench tasks. And then over the last half year, with the help of the Terminal-Bench community, we converted 80 language model benchmarks, many of them agentic, into the Harbor format so that you can evaluate many agents in the same API. And we are currently wrapping up a nice paper on what we learned from doing this, like a meta evaluation. That thing it's big. This is my first paper with over 100 authors, so we will probably put it out sometime in June.
Question.
Yes.
So it's nice to see the output accuracy, but there are lots of the other agentic capabilities such as memory management and maybe instruction following or implementation. So do you have some sense on evaluating this fine-grained aspect of agentic capability?
Good question. So maybe two thoughts on that. I think these are good to evaluate, and some of the things we adapted in Harbor are benchmarks that focus more on instruction following. For me, in the end, memory management, instruction following, they are means to an end. And what I want to measure with Terminal-Bench is sort of like,
how all of these skills come together and how good are the agents in the end in solving complex problems. And it measures some amount of instructional following and so on. Not as precise as some instructional following benchmarks, but it's cool that we can test sort of like the end-to-end ability of agents to solve complex problems. Cool, so we are almost done now. So let me just quickly go through the ongoing projects here. OpenThoughts for agents, this will come on archive soon. Here the focus is, okay, we learned a lot from OpenThoughts for reasoning models, but in the end, I think these reasoning benchmarks, let's say, are medium interesting. I think they are good for testing reasoning capability, but it turns out making better reasoning models does not actually lead to better agents. So for OpenThoughts agents, we sort of like redid this experimental approach, now with a focus on the agentic benchmarks. Like the short summary here is that our OpenThinker agent model now is state-of-the-art among open data models on Bench, Terminal-Bench, and so on. So same high-level approach also works for agentic tasks, but you do need to use different source data sets and so on. And then the follow-up work on the Terminal-Bench side is twofold. So one thing we are doing right now is building Terminal-Bench 3, because as I said, Mythos almost fully solves the benchmark. We expect that in the next 1 or 2 months, probably models will fully saturate Terminal-Bench. So we need a follow-up. And we've been working on this now for a few months. I think we have sort of like on the order of 30 tasks now already in TB3, but we want to get to 100 tasks again, or at least close to 100. So if you have ideas for really challenging tasks that you want to evaluate the models on, please help. Like make this a Terminal-Bench task, join the Discord. We are very open to contributions still. So by now we have lowered the bar, or maybe the bar has gone up, it's unclear. The number of tasks you need to contribute to be a co-author on the paper now is 1 task, because the tasks are harder to build and we want them to be very high quality. But if you have any ideas, please send them our way. And then the other thing we are doing is a version of Terminal-Bench focused on computational workflows coming up in the sciences. And I think this is interesting for 2 reasons. First of all, I want to make sure that as these models get better, they also help our colleagues in the bio department, chemistry department, and so on, and accelerates their scientific work. And measure this to make sure the models get better on that dimension. And the other thing I think that's interesting here from a machine learning perspective is that these Terminal-Bench and Bench tasks, they often work with like very popular software packages. Like for instance, Bench, if I remember correctly, has more than 100 tasks. All of them in the, more than 100 tasks in Bench are working with the Flask repository, like a popular Python web server. And sometimes John, one of my PhD students, who is a co-first author on Bench, he sometimes jokingly says, well, Benches maybe should be called Flask Bench because it's all about Flask. And there's so much in the training data of these models for popular Python repositories. So one hypothesis is the models are so good at this because they've seen so much training data around Flask. And what I want to see with Terminal-Bench is like, how good are the models at these super niche, sophisticated computational workflows that only 3 scientists in the world have ever worked on? And I think this is a really great test for seeing how good are the models at generalizing to much more niche workflows with much less coverage in their training data. So same story here, very open to suggestions. Terminal-Bench science is still in an earlier stage. I think we have 3 tasks right now. Overall, we need to learn right now, how do we reach out to the science community and get the scientists excited to contribute tasks? Because we have all the AI expertise. We have like 0 in-depth expertise in these science domains. So we need to bring these 2 together. If you want to learn more about any of these or help us, help is very welcome. Go to Terminal-Bench or T-Bench AI. And that's it. Thanks for listening.
Any questions from the audience? Yes.
I'm kind of curious about maybe your sense of like how you might be able to measure, or maybe if you think it's worth doing like some kind of like human AI collaborative agentic workflow. So one example I can imagine is like, the tasks that you specify in these benchmarks, they're usually well-defined and well-scoped, there is a clear answer, a way to evaluate it. But like, as a human, maybe like I'm entering some new discipline for the first time. I may not know everything about like how to even approach this problem. Maybe I just have a high level idea, but not understand the specifics. So there's like a lot of human error and like maybe my understanding and like the user's understanding as well as to what like needs to be built. And do you think agents should be like somehow designed with that particular workflow in mind, or do you think they should just be like they just go off and do their own thing and then only like return to the user when they think they're done?
Great question. And I think the answer very much is both. You're totally right that often people use the algorithms in a much more interactive way than what Terminal-Bench tests. And I think this is very much worth thinking about. How do we build benchmarks with more human in the loop? In fact, Sean Yang, who I just mentioned, the PhD student in the bench, he wrote a nice position paper on this recently, calling exactly for more benchmarks, do software engineering and so on with a human. Like one approach would be to say, okay, we have sort of like one language model simulating a user, and then the language model that you evaluate as an agent needs to talk to the user simulating model and so on, go back and forth and elicit some information. I think many questions how to do this well in detail. I think it's a really good research direction. I think simply testing how good the models are at doing work on their own is also meaningful, because in the end, we would like the models to be able to work independently for long durations. And I think this is what we are measuring in Terminal-Bench. In terms of design philosophy, what we like to ensure in Terminal-Bench is as objective grading as possible. Currently, we feel that these human-in-the-loop things with a language model as a user simulator, for instance, can be a little bit trickier to get right. And maybe then there's some reward hacking going on where the agent convinces the user to just give the model a solution and stuff like that. We don't want that. So this is why for Terminal-Bench, we minimize the use of LLMs in the task itself outside the agent. But I think both are really good dimensions to work on.
Yes, that question. So for Terminal-Bench, you see that it can easily get saturated. So it's by itself defined as a static benchmark. Do you have any sense that we could grow this as a dynamic benchmark where we have like a lot more diverse input or diverse tasks, and we can like allow evaluate
Yeah, 100%. I think this is a really nice direction for research, how to assist humans or maybe even build these benchmarks in a fully automatic way. Because as I mentioned, this is a ton of work. And right now we're doing this because we can still do it. I think it will get harder and harder as the models get better. And we want this very high quality bar. So my primary worry would be if we use directly AI generated tasks, then the quality is unclear. And as I mentioned, we put so much work into manual verification because even experts, it's easy for them to make errors, and then there's a slight mismatch between the task description and the test, and then the model does it correctly, but the test incorrectly is too strict in some way. So this is why we do this mostly manually. And actually in Terminal-Bench 2, we observed that last year the models were not good enough yet to make task. We actually had like a no AI rule for Terminal-Bench 2 because we got some AI submissions and they were mostly bad. Now for Terminal-Bench 3, the models have gotten better, so we're obviously more open to people using agents in their development. But for instance, we want that the instruction file is still 100% human written. But I think as a research direction, seeing how you can build these tasks is a great question. For instance, in the science context, we've been wondering, can you build TB science tasks automatically from archive papers that have an associated GitHub repository? Because then you could ask them like, oh, okay, there's this analysis that you do in the paper. They even have the code here. Can we somehow use Opus in order to set up a task, reproduce this paper, and then use the GitHub implementation as the ground truth that you can check things against? Just a high-level idea, but I think it's a good research direction.
Kind of like following up on this. So basically, there's a lot of cool tasks, at least, the ones I use agents for, which basically I have an idea that relates to some evaluation or some whatever fine-tuning of the model that requires to exit the sandbox or whatever the agent lives in and use resources external to what I'm using, which currently seems to I can map this to running a terminal-bench on a sandbox. And I think more important than that is that there are cool tasks that require expensive resources. Make that as an evaluation task very expensive.
Yeah.
How are you thinking about those? If I don't know if you have some of those in Terminal-Bench 3, but there are important tasks that are expensive to even evaluate.
Yeah, okay. Great question. We sort of have two perspectives on this. One is that for Terminal-Bench, we want to keep it as something where you can run these 100 tasks and it's not immediately making you bankrupt. So let's say keep the cost per task in the let's say maybe $100 range, which is already 100 times 110K for a single run. But we have increased the size of the virtual machine, and we also support and harbor now VMs with a GPU. So for some of the tasks, the models can use a GPU. At the moment, we are not fully sure yet if we keep those tasks in TB3. If it turns out we can get away without GPU support, it's easier for people to work with. There's always this trade-off, the more complex you make the environment, the harder it is for people to run your benchmark. And so then there's this thing, okay, there are some task suggestions we are getting, which are really interesting, but they are just way bigger than what you can do in $100. And for that, we are currently setting up what we call Terminal-Bench challenges. And the idea here is that it's sort of like an N equals 1 benchmark. Yes. The first version will just be 3 challenges, and it's something on the order of rewrite this Python library in Rust and make it really fast.
Yeah.
And then I don't care what people do, honestly. I just want at the end that you have written this, or that someone, could even be a human, won't be a human because it's too much work, that someone has rewritten this library in Rust and it's really fast and passes all the tests.
Yeah.
And then we can make a leaderboard just for this one task around how expensive is it or how fast is the resulting library. So I think this is increasingly where some of these things will go. And it's sort of each task by itself will almost be a benchmark and people can compete on that. So if people have ideas for TB challenges, also very welcome.
Awesome. Thank you. Any other questions? Let's thank Ludwig again.